They have pretty ample.
All right, stop talking. My name is Cameron Bai. I'm a master's student here at CCBN in the Robert McDonald's lab. And I'd like to introduce you all to the first talk in our summer speaker series. The summer speaker series is an annual event where for the summer semester, all of our faculty and postdocs, well not all of them, but a lot of the faculty and postdocs get to present their work to the members of the neuroscience department. And so for the first talk, we have Dr. Artur Luček. He got his PhD at Jagiellonian University in Poland. He was awarded several fellowships in the Netherlands, France, and Italy. He did postdocs at Yale University and Rutgers University, and he's been here at the CCBN since 2009. So I'd like you all to give a round of applause for Dr. Artur Luček.
Thank you very much for giving me the opportunity to share with you my research. Usually I'm sitting in my room separated from you, so today it will be a chance for you to know what I'm doing when I'm locked in my office. I will be telling you some story about packets, and soon I will go to that, but always I like to start my talk with reminding you that, we know that brain has this many different areas, and for me, we also know that areas are not randomly organized, but they have some special organization. For example, in auditory cortex, there is what is called tonotopy, that on one side of this auditory cortex neuron responds to low frequency tones, on the other side to high frequency tones. And what is really amazing, at least to me, is that in this little rat brain, all the parts of the brain what we have are also, exactly in the same position in rat brains. And there's maybe some differences, like this big olfactory bulb, because rat is living in a dark environment, so smell is more important. But of course, we also have in the front olfactory bulb just much smaller in proportion. The very important thing to realize is that whatever we learn about those little rat brains, it gives us almost directly information how our human brains are working. So I showed you that we know that certain brain areas are doing certain things, but what we really have much less idea about is how this neuronal circuitry in cortex is working in any given place. So each neuron, as you know, has thousands of connections, and we have billions of neurons, so it is highly interconnected network. And how the signal propagates through those networks is really very poorly understood because of the complexity of this problem, that this neuron will send information to tens of thousands of other neurons. Each of those neurons will send information to tens of thousands of other neurons, and how to understand how this information is processed is a very challenging view. What we are doing is that to try to get some glimpse how this processing is done, one way to do it is to put some probes inside brain and listen to some of the neurons. And here is a picture of a rat with two of such probes in the prefrontal and somatosensory cortex. Here is a cartoon of one of sample probes, and it shows that each of those recording sites is like a little voltage meter, and gives us information when each of those neurons is active. So if such probe, for example, is in auditory cortex, we can now see which neurons are responding to which tones. And for example, is this neuron responding always together with this neuron, or maybe this neuron is responding to some tones and this is to other tones, or maybe this neuron is firing earlier and this is always firing later. What is the propagation of signal through this circuit? So by sampling with such probes from many neurons, we are getting a little bit of understanding how this auditory wave is later transforming our cortex to give us perception of sound. So here is again cartoon of a probe of probes probing from layer in cortex. So if we look at activity of just one neuron, this is 2 seconds, and we can see that when this neuron is active. But what is much more informative is if we can record not one but many neurons. So now we can see that even that this bottom neuron was silent here, other neurons are not silent in this part. So there are those coordinated patterns of activity, but each of those patterns seems to be different from previous pattern. So by looking at not one neuron but at tens of neurons, we are getting a little bit of better understanding how this signal in cortex is processed by neurons. One interesting thing is that here is recording, for example, from auditory cortex in anesthetized animal, and this animal is in soundproof box, and we are presenting just pure tone here. And what you can see right away that even in this auditory cortex, in this part of the brain designed for sound processing, when there is complete silence, this part of the brain is not silent, it's all the time doing something. And this big mystery, what is this spontaneous activity doing? Because each of those action potential takes energy, so brain for some reason is devoting a lot of energy to process some information which we have no idea what it is. And when you think about it, only very small percent of the time we are really responding to some external stimuli. It's estimated that 90% of this internal activity is this spontaneous activity, not directly driven by any stimuli. So it is similar like in physics, you have this 90% of universe composed of this dark energy and dark matter, and we are using word dark because we don't know what it does. And it's similar here with the spontaneous activity, it is there, but we have no idea or little idea what it is really doing. So how to approach this problem? Well, if we have, for example, some code and we want to decipher this code, one of the approaches is just to look at the statistics, try to see if there are some repeating patterns, if there are some regularities in this pattern. And we can note, for example, that certain symbols may more often than by chance co-occur to each other. And if we have suspicion that each of those symbols may be coding for a single letter, then we can now, if we have much longer text, we can look at those statistics and we can compare it to how often different letters co-occur in Polish or English language. And based on this, it is possible to decode such code and to find out what was the original message. And here I encode this. I never came upon any of my discoveries through the process of rational thinking. And this Albert Einstein thought, so too bad to my approach to science. But the main message is that by doing the statistical analysis of this of this coded signal, it is possible to recover what was the original message. And similar approach can be used to neuronal data by looking if there are some repeating or some statistical dependencies between neuronal activity. It can give us some insight what is the meaning of those patterns. So here is another example of activity recorded from 40 neurons. So each line is activity of one neuron, and here is 2 seconds of data. And again, here is spontaneous activity, here is evoke activity. And this is in a non-anesthetized animal. This is animal passively listening, and here it is animal which is probably very bored with this listening to pure tones. So you see this kind of long periods of silence. This is called synchronized type of activity, which also occurs when we, for example, sleep. So what you can see is that what people observe a long time before is that in such synchronized state, there are those bursts of activity, and this is why this state is called synchronized, because neurons tend to fire in the synchronized burst. And what we noticed when I was working at Rutgers is that if you look more carefully at the structure of those bursts of activity, you can notice that statistically some neurons tend to fire earlier and some tend to fire later in a majority of bursts. And moreover, if you look at the sequences evoked by stimuli, the sequences seems to be quite similar. So neurons which spontaneously are active earlier in this spontaneous burst, they also are easier to be activated by different stimuli. And I will talk about it in more details in few slides. To somehow summarize this figure, it seems like in the synchronized states you have this burst of activity, and each of bursts have this more or less similar sequential structure. Not identical, but statistically similar. What happens when rat is more engaged, when for example we are focusing our thoughts on solving some problem, our brain gets in this so-called desynchronized state. So here you see that activity is this continuous, you don't see clearly any of the bursts, and this is called this desynchronized brain activity. But when we did some more careful analysis, we also found that there are some bursts, and those bursts are more often occurring than expected by chance. So with some quite a bit of computer crunching, what we discover is that it seems like this desynchronized state is composed of the same type of packets as of this burst as the synchronized state, but those packets are occurring very close to each other, they are even overlapping, and because of that it gives this perception of continuous activity. But in fact, here the seemingly continuous activity is divided in these packets. And if you have any questions, please stop me anytime. If I don't look at you, you can just shout, and I'm happy to answer any questions. And this is a kind of outline of the story which I will be telling you today, and it took over 10 years to develop it, and here are just a few main publications about it. So first I will tell you about this tone-evoked burst, of these packets evoked by stimuli, of those sequences evoked by different type of stimulation. So here in auditory system, for example, if you look at activity of neuron and present different tones, you will find that neurons tend to fire to some tones, but not to other tones. So this neuron is firing to, let's say, 6 kilohertz up to 40 kilohertz, but it's not firing to low frequencies. Other neurons, for example, are firing to, this firing is firing to similar range of tone, this is firing to mostly to these higher tones. But what is interesting to notice is the following, that this neuron, even that it may slightly change timing and firing rate to different tones, it consistently fires earlier than, for example, this neuron or this neuron. And this neuron, for example, seems to be firing more to these tones around, let's say, 30 kilohertz. and it's firing slightly earlier and with higher firing rate, but nevertheless, still it's not firing as late as, for example, this neuron, or it's not firing as early as this neuron. So if you record from, let's say, many of such neurons, then later what you will have this sequential activity. You will see that this neuron starts the sequence, this is firing in the middle, and these neurons are firing in the end of the sequence. So here is some data from 90 neurons recorded simultaneously, and this is, so here in grayscale it's counted what was the level of activity, and here with the red dots I plotted what was for each neuron the average response time, and you can see that some neurons tends to fire earlier, some later, and it seems like it is kind of a continuum, that it is not two groups but rather continuum, and again I will talk about it in more details. And this is what I showed you for auditory cortex. When I did survey of literature, it seems to be quite abundant phenomenon across other cortical areas, but for example in somatosensory cortex, if you have people did experiments where they were applying different tactile stimuli. For example, they either touch digit or they touch palm of the rat, and they observed that to different stimuli this neuron was responding slightly different, but here it was a little bit longer, with longer latency. So here on this axis are different trials. But they also found that other neurons seems also respond differently to different stimuli, but they are always tend to fire with longer latency. So it's not that this neuron to different stimuli suddenly starts responding with this late latency. It's rather that it's only slightly changing each firing rate and latency. And so again, you have these early neurons and late neurons. Similar in olfactory bulb, olfactory system, there was shown that if you have here different colors denote two different odors, that for those two different odors, neurons respond with a slightly different pattern, but overall the sequential structure for both odors is more or less similar. So it's similar sequence, just small variation on this sequence are informative what is the stimulus. Okay, so I showed you that when we present some stimulus, we will have some neurons consistently firing earlier, some later. But also what is interesting is that even without any stimuli, if we look at this spontaneously evoked burst or these packets, then the sequential order is similar to this tone evoke or stimulus evoke patterns. And here we did some statistics. So here is the picture which I showed you before, response of neurons to tones. And if we plot neurons in the same order, when we trigger on those, detect those spontaneous bursts, we see quite similar sequence. And the one question is, okay, those pure tones are very simple stimuli. What happens if we present some more natural stimuli, like, for example, monkey vocalization or some insect sounds? And we did this, we play some natural stimuli, and we also found that for each stimuli the sequence was slightly different, but overall the pattern was very similar. And distribution of points along this diagonal line, it shows that for tones and natural sounds, it was very similar sequential order as for spontaneous packets. One interesting question is there any relation between those spontaneous packets and those stimulus evoked packets? Is somehow this information can affect what is happening here? And it is one of the experiments which we did here, and Edgar Bermúdez-Contreras and Andrea Palacio-Sheinman did these experiments and data analysis. So here what we did is that we had rat and we applied some simple tactile stimulation to the forepaw, and every stimulation evokes some sequential activity as expected, and if we sort neurons we saw some sequences. But if we look more as we saw before, for what was the sequential order before stimulation, let's say 10 minutes before applying the stimuli, we saw that not exactly the same, but still similar sequential order was presented. But now, after presenting for 10 or 20 minutes this repetitive stimulation, what we did is that now this spontaneous activity following the stimulation is now recapitulating this experience. So now the sequences are much more similar to these evoked sequences. Those spontaneous packets are somehow reorganized to more represent those evoked patterns which were presented here. So it seems that when we are learning something, we are reorganizing those packets, and the sequencing these packets in the spontaneous packets is somehow recapitulating what was done before. And it is a little bit similar to this replay phenomenon which Bruce McNaughton discovered. Okay, so here is again picture of this neuronal activity, and here what I'm showing is 3 different brain states. So it is recording from the same rat, just at some point rat has this synchronized brain state, this kind of drowsy, sleepy state. Sometimes spontaneously his brain is getting more desynchronized, and it's more correlated with this attentive state. And as I showed you, and so we did some quantitative analysis to see if the sequences here in this synchronized brain state are similar to sequences in desynchronized brain state, and the distribution of points along this diagonal, it shows that indeed it is, that those sequences in both brain states are similar. So basically it was indications that this seemingly continuous activity in this desynchronized state, when brain is more active, it means that there is just more packets sent. So you can imagine that here when rat is just sleepy and is not processing much information, only few packets are sent. But here when this rat is thinking, let's say, intensively about something, a lot more information has to be sent. So there is a lot of packets sent one after other, and it creates this impression of continuous activity. But in fact, each of those packets has still consistent sequential structure. So one thing what was puzzling is the following, is that each of us know that if you present stimuli and later look at activity, then you always see this big stimulus evoke response. So here what I'm showing you is that this stimulus evoke packets, they seems to be quite similar to spontaneous packets. So it is, we don't see here some bigger stimulus evoke activity. And so here is example of such typical stimulus evoke activity. Then when we present stimulus, let's say 100 times and average it, and in average we see this big evoke response. But when we look more closely what happens on the single trials, so here each of those lines is multi-unit activity, so it shows what was the total activity in a given cortical area. What we see is that at those 3 different trials, which are shown here, those evoke responses are not bigger than some spontaneous packets, but rather when you average it, because stimulus always is evoking those packets, and in average you will see this big peak, And here, because those times of those packets are kind of random, they will average out to much lower baseline. So it isn't that this stimulus evoke activity is much bigger, it is just because we are doing this averaging and looking at averages, we are getting this picture that it is bigger, but in fact, when we present stimuli, those packets are no different size than spontaneous packets. And we did some quantifications to quantify. Okay, the other interesting thing is I showed you that some neurons tend to fire earlier, some later. And here is an example of two neurons, one firing earlier and one firing later. And what you see here is that this neuron which fired earlier, it seems to be firing less selectively. So here are responses, multiple trials, 50 trials to different tone frequencies. So you see that this neuron 1, green neuron, is responding with more or less the same pattern to each of those tones. But this neuron 2 is much more selective. It's only responding to a particular tone of 12 kilohertz. Also, what you can notice is that here, this first neuron, the responses are much more tighter. It is much more constrained to some small period of time. And here, if we repeat it across trial, this is much bigger jitter in activity. So if we would look what is the spike reliability, so how reliable spikes are evoked by stimuli, we will see that those early neurons on the beginning of these packets, there is this big spike reliability, and later there is this bigger jitter, so the spike reliability is decreasing. But stimulus selectivity is, on the other hand, increasing, that these neurons are the least selective, and those neurons which are active later in packets are getting more and more selective. And it was found, for example, in not only auditory system, but across other sensory systems. For example, in visual areas, it was found that those first neurons are responding, are having information only that this is some face. But the neurons which are active later are saying, oh, this is face of monkey George or some other monkey. So those neurons contain information about specific identity of the monkey, and this is just saying, oh, this is face of animal. So this kind of increase of selectivity with time in packets seems to be quite consistent across modalities. And this has some important implications for neuronal coding. So a lot of people are thinking, what is the codes that brain is using to cover information? And some suggest that this precise spike timing, others suggest that spike timing is less important, that is more firing rate. And what it seems is that both things are used simultaneously in this packet, that spike coding, the spike timing seems to be much more important on the beginning, that small differences in timing of those early neurons can convey information, but here, for these other neurons, it's mostly information how many spikes it fired. Not timing, but in how many new spikes it fired, so it is more what is called firing rate coding. So for people interested in neuronal coding, it is nice because it shows that in single packet, both type of codes are used. So to somehow summarize this part, what I was trying to say is that if we have two stimuli, so here response of 4 neurons to different stimuli, the overall sequence will be very similar for each stimuli, but some small differences, it will be what will be encoding different stimuli. So, and those early neurons will be very little change in the activity between stimuli 1 and 2, but for those late neurons, it will be quite big changes in number of spikes, and they will have much more information about a given stimulus. So this what I showed you, it's a little bit reminding me how engineers design information transfer over internet. That if you write some email, hand, this email is not sent in continuously, rather it is divided in some packets, and each packet has what is called header. It is information where to send this packet, and this other part, what is the content of this information. And it seems to be quite similar what is happening in the cortex, that this information is divided in those discrete packets, and the neurons which are active earlier, they have some general information. Let's say this is auditory information, let's process this information along